As a start point for intermolecular forces, it's worth breaking down the term to help clarify our understanding. Firstly, the word inter tends to refer to between something. Of course, molecular is referring to molecules, and in the case of intermolecular forces, the forces is referring to weak electrostatic forces of attraction. In IB chemistry, there are three types of intermolecular forces that we need to be aware of. Firstly are London forces, also known as dispersion forces. Secondly are dipole-dipole forces. And thirdly is hydrogen bonding. And there's another term you'll see in the syllabus, which is van der Waals forces. And this term is simply an umbrella term for any combination of the first two types of intermolecular forces. So, for example, London forces on their own are a type of van der Waals force, the same with dipole-dipole forces, and also a combination of London and dipole-dipole forces. So let's start off by looking at number one, which is London forces. The start point for explaining London forces is understanding that electrons are moving randomly in atomic orbitals. And you can see this in a simple visualization like this. Because of this random movement, at any given time I could have more electrons on one side of this atom compared to another. So at that very instant we have a dipole in the atom or molecule. Of course, in this diagram we're looking at just an atom. To demonstrate this, we can take 3 screenshots of my GIF above and have a look at the position of the electrons at that moment in time, or that instant in time. In this first example, I can see there are more electrons on the left-hand side of the molecule at this instant compared to the right side. So I can add partial charges to show the dipole existing at that moment in time. In the second image here, I can see there are more electrons to the bottom right side of the atom compared to the top left. So again, I can add dipoles to show this. In the third screenshot, I might add the negative dipole or partial negative charge to the top side of the molecule instead of the bottom. Of course, because these electrons are continuing to move, these dipoles only exist for a fraction of a second before the electrons have moved to new positions. Once an instantaneous dipole is formed in an atom or a molecule, that can then affect nearby atoms and molecules in a similar manner. We say that an instantaneous dipole can induce or cause a dipole in a nearby atom or molecule. In this example, let's continue focusing on atoms. Here is the atom we saw previously, and in this case, the electron density is more to the left side of the atom, hence the partially negative side on the left. If I place this to an atom which currently has no dipole, then the partially positive side of the atom on the left will attract electrons from the atom on the right to its left-hand side, causing a dipole. So for a very short period of time, I now have 2 atoms next to each other that both have a dipole. And as we know, opposite charges attract. So we will see a weak force of electrostatic attraction between the 2 atoms. This only lasts for a fraction of a second before the random movement of electrons eliminates those dipoles. And that's why London forces are considered the weakest of the intermolecular forces we need to know about. Because all atoms and molecules contain electrons, they will all experience London forces between themselves. And a greater number of electrons in atoms or molecules will lead to stronger London forces, because we can have stronger dipoles, or instantaneous dipoles, to start with. Let's now have a look at the second type of intermolecular force, dipole-dipole. Dipole-dipole forces are caused by the electrostatic attraction between molecules with permanent dipoles, otherwise known as polar molecules. For example, if I take two hydrogen chloride molecules and place them next to each other, I can see that already, because chlorine is more electronegative than the hydrogen, we have a dipole, permanent dipole, on each molecule. So these molecules will orient themselves so that the partially positive and partially negative sides of each molecule are next to each other. And here you can see we have a weak electrostatic force of attraction between those molecules. In this case, because the dipole is permanent, the intermolecular force is going to be stronger than the London forces we saw previously. Here's a second example of some hydrogen sulfide molecules. And again, you'll see each molecule has a partially negative side at the top near the sulfur and a partially positive side near the bottom where the hydrogens are sticking off. Again, we see a weak electrostatic force of attraction between the partially positive side of one molecule and the partially negative side of the other. And as we mentioned already, dipole-dipole forces are stronger than London forces because these dipoles are permanent. Of course, the more polar a molecule is, the stronger the dipole-dipole forces will be. And this is because the magnitude or the size of those opposite partial charges are greater, therefore we will have greater electrostatic attraction between them. Finally, let's look at the third intermolecular force, which is called hydrogen bonding. The first important thing to note here is that although this intermolecular force is called hydrogen bonding, it is not actually considered a type of chemical bond. And although it's the strongest type of intermolecular force, it's still about 10 times weaker than your average covalent bond. Similarly to dipole-dipole forces, hydrogen bonding is caused by the electrostatic attraction between polar molecules. However, we need to be more specific. It's actually between highly polar molecules that contain a nitrogen, oxygen, or fluorine bonded directly to a hydrogen. Let's look at 3 examples to explain why this is. Firstly, let's consider 2 ammonia molecules. You can see that, as with dipole-dipole forces, we are talking about polar molecules. In this case, the nitrogen, which is more electronegative than hydrogen, is the partially negative side of the molecule, and the hydrogen sticking off the bottom would be the partially positive side of the molecule. So we know there's going to be an electrostatic attraction between the partially positive and negative sides. So why then do we categorise this as hydrogen bonding and not simply a dipole-dipole force? Well, when considering nitrogen, oxygen or fluorines, they are firstly very small atoms and also the most electronegative atoms in the periodic table, causing a particularly strong dipole when bonded to a hydrogen. You'll also notice that I've drawn a lone pair of electrons on the nitrogen, which adds additional negative charge density to my nitrogen atom, which is already very electronegative. So the electrostatic forces between these 2 polar molecules are particularly strong compared to other molecules. A second example might be 2 molecules of hydrogen fluoride. And again, this is categorized as hydrogen bonding because fluorine is very small and very electronegative, so we have a very polar molecule. We also have, in this case, 3 lone pairs of electrons on the fluorine, making its partial negative charge even stronger. The final example we might look at is water. And as explained with the first 2 examples here, this is also categorized as hydrogen bonding because we have a very small, very electronegative element in oxygen, which also has at least 1 lone pair of electrons, making that partial negative charge even greater. As a tip for exam questions about intermolecular forces, anywhere that you can find in a molecule a nitrogen, oxygen or fluorine atom bonded directly to a hydrogen, that will contain hydrogen bonding. Let's now summarize the key points from this video. Firstly, it's worth mentioning that intermolecular forces are all weak electrostatic forces of attraction between molecules, although London forces can actually also between atoms. There are three types we need to know about: London forces, also known as dispersion forces, dipole-dipole forces, and hydrogen bonding. Remember, hydrogen bonding is not actually a form of chemical bond, it's just given that name because it's the strongest of the intermolecular forces. Of the three, London forces are the weakest, dipole-dipole somewhere in the middle, and hydrogen bonding tends to be the strongest. London forces are caused by the attraction between an instantaneous dipole and an induced dipole. Dipole-dipole forces are caused by the attraction between permanent dipoles on polar molecules. And finally, hydrogen bonding, a little bit more complicated. It's caused by the attraction between a lone pair of electrons on a very electronegative atom, that's nitrogen, oxygen or fluorine, and a highly partially positive hydrogen on another molecule. Covalent substances can have just one type of these intermolecular forces, or perhaps two, or maybe in some cases three. Hopefully, this video is of some help.